According to energy conservation law, we know the initial total energy should be equal to the final total energy. Initial total energy here is the total energy before the pilot shut off the engine. And final energy here is the total energy when the lunar module landed on the surface of the moon. So if we expand the equation, we have Ki plus Ui is equal to Kf plus Uf. K is the kinetic energy, and U is the gravitational potential energy. If we expand the equation for each energy here, we have 1/2 mvi squared plus mghi is equal to 1/2 mvf squared plus mghf. Vi is the initial velocity, which is the velocity of the lander relative to the surface at a moment. And we know hi here is the height before the pilot shut off the engine, which is the greatest height we are looking for to determine. And VF here is the final speed, which is the speed when the lunar module landed on the surface of the moon. And HF here is the final height. So we know the final height should be equal to 0 since it landed eventually. So now we have 1/2 mvi squared plus mghi is equal to 1/2 mvf squared. So if we do an arrangement here, eventually we'll have the initial height, which is the greatest height which pilot could shut off the engine is equal to VF squared minus Vi squared over 2g. So now for the first case, you were saying that the initial velocity, which is the velocity of a lander relative to the surface at a moment, is given as 0. Therefore, have the initial height, which is the greatest height we can determine, is equal to Vf squared over 2g. So we know the final speed should be equal to 3 meters per second, and the acceleration of the gravity on Moon is 1.62 meters per second squared. So now let's plug in these values back into the equation to determine the greatest height, which is equal to 3 meters per second to the power 2 over 2 times 1.62 meter per second squared. And this will give us the greatest height is equal to 2.8 meter. Now let's take a look at part B. Part B was saying that the velocity of lander relative to the surface at a moment is 2 meters per second downward. So we consider the downward direction is negative direction, and the positive direction is the upward direction. Therefore, have the initial velocity is equal to negative 2 meters per second. So now we know the final speed is 3 meters per second, and the acceleration gravity on Moon is 1.62 meters per second squared. Now we can plug in these values back into the equation to determine the greatest height at this case, which is equal to 3 meters per second to the power 2 minus negative 2 meters per second to the power 2 over 2 times 9.8 meters per second squared. Sorry. We should use the acceleration of gravity on Moon, which is 1.62 meter per second squared. This will give us the greatest height, in this case, is equal to 1.5 meter. So now let's take a look at part C. So for part C, it was given that the velocity of lander relative to the surface at the moment is 2 meters per second upward. Since it's upward, therefore it's positive 2 meters per second. So now let's plug in the values back into the equation to determine the greatest height in this case, which is equal to 3 meters per second to the power 2 minus 2 meters per second to the power 2 over 2 times 1.62 meter per second squared. And this will give us the greatest height is also equal to 1.5 meter. And these are the answers for this question.